who
It's
shall
hard
be
to
talking
pronounce.
about self-similar solutions in dark fluid cosmology.
Yes, thank you very much. I'm Balazs Szigeti, and I'm from Hungary, and I would like to present this lecture as the last presenter today. So what can a self-similar solution give us about dark fluid cosmology? Self-similarity is an interesting question. It's used widely in Newton dynamics from the 1940s, the famous Godoli-Landau-Stanjukovic problem. But how can we apply in this kind of situation in general relativity and in cosmology? So in Newtonian gravity, the scale-free nature of Newton gravitational interaction in Newtonian gravity and general relativity is well known. And self-similarity can be applied easily, straightforwardly in Newtonian system, but it's not so straightforward in general relativity. But what is the reward? So when we apply some matter in the Newtonian Einsteinian equation, we have to know something, how to classify the solution which we can get. And self-similar solution can provide the values tool to express how the different solutions relate to each other. So how can we express this self-similarity in general relativity? Self-similarity of space-time can be defined by these homothetic vector fields, where this L is the standard Lie derivation, which is a special kind of the well-known Killing vector fields. So this is easy when we only consider vacuum solutions. But unfortunately for the general relativist cosmologist, space is not just vacuum, so we have to add some matter fields. When we consider non-vacuum solutions, self-similarity appears two kind of mode. The first one is the self-similarity of the space-time. The second one is the self-similarity of the matter. And sometimes matter is kind that they break partially this self-similarity, and we use these kinematic self-similarity vector fields to describe this partial breaking of the self-similarity. So as you see, we have two equations, one for the projection tensor and one for the for velocity, and we have two constants, the delta and the alpha. And delta and alpha are dimensionless constants, and it's kind of the similarity index. When delta is 0, we can get back the well-known Killing vector fields, and the other kinds are different kind of self-similar solutions, which provides different kind of solutions of the Einstein field equation. So we consider the general symmetric space-time where the unknown function, the phi, the psi, the r, and the sigma are function of t and r, or k and theta. And we adopt the co-moving frames, which is usual in the cosmology. So the general kinetic self-similar vector can be written this form where h1 and h2 are unknown function, and we would like to obtain this function using this method. And H1 is the case where the solution is orthogonal to the fluid flow, and H2 equals 0 is when the solution is parallel to the fluid flow, and we have the most general case where nobody is 0, so it's tilted. And we can transform the kinematic self-similar solution vector field into this kind of form. So as we consider, So as we consider different kind, we use this corresponding line element, and in this case, all of the functions which we are searching for are function of the similarity variable, which is r per t in this kind of case. And as we see, we have different kind of similarity variable, which lets us different kind of solutions. We considered 3 of the cases. The first case, which is not on the slide, is the vacuum solution. The second kind is the perfect fluid, which is a known equation. And the third time is a general Chaplygin gas, which is used to describe this dark fluid, which is a mode to unify the dark energy and the dark matter. And as you can see, we obtain different kind of solutions, which is relates to different kind of well-known solutions of the Einstein equations. And as we can see that all of the solutions which can be existed in this kind of Chaplygin gas dark fluid model leads us to the well-known flat Friedmann-Robertson-Walker-Lemaitre metric, or the Lemaitre-Tolman-Bondi model, which is all known, or just the all-static solution, which is not so interesting for us. Self-similarity as a concept has been applied to many parts of the physics, and self-similarity in generality is derived from the concept of homothetic vector fields, and these kind of solutions can be used to classify the solutions which we can get from one type of matter fields. And a future question for us is some more exciting cases like conformally coupled Higgs models, or kinematic self-similarity in Einstein-Maxwell equations, which is an maximum motivated solution. Thank you very much for yes, thank you.
So, thank you very much for keeping the time. And questions?
Hi, thanks for this. So do you have in mind a particular scenario where this would happen, like in some sort of history of the universe, cosmology, where the criticality would play a role?
So we just started to work with these models, so we have only these solutions where we can classify, but we would like to apply some astronomical data to see what these kind of solution leads to the astronomical observations.
Yeah, because there was a role of this in cosmology that was pointed out by Jens Niemeyer a while ago. It's the only one I know, the use of this sort of self-similarity, but yeah. Maybe I can post the paper in the Slack chat.
Thank you.
Thanks.
Thank you very much.
Maybe one question in a similar direction. Could you comment a bit more on your last point, your future question? Sorry, if you could go back to the conclusions.
Yes.
Right. So your last point, what you mentioned as future question, and there you say axion motivated. Could you comment a bit more on what you have in mind there? So
in this case, we would like to solve the Einstein equations as the electromagnetic fields, which appears on the right side of the Einstein field equation in the energy momentum tensor, are also depend on this similarity variable, which we can get from the metric of the system. And these methods is good because we could reduce the nonlinear partial differential equation system into an ordinary differential equation system, which is usually solvable, at least numerically. So they can provide information about how these Einstein-Maxwell solution can relate each other in some restricted mode.
Okay, good. So I still cannot make the connection to the axion.
Yes, so there are models which relates that axion can be related with dilaton Einstein-Maxwell systems. So it's a model for axion.
Okay, good.
Thank you.
Thank you.
I will allow one more question. Who would like to ask the last question for today? Okay, then let's thank the speaker again.
Thank you very much.
And once more for both speakers of the session.